Hi everyone, I am Gunnar Grosch and welcome to another edition of Serverless Chaos, where we look at chaos engineering for serverless environments. So this week we're gonna look at disk space failure and see how we can use that in our chaos experiments. But first, let's kick it off the way that we usually do and look at what we did last week. So in the last video, we started off by looking at the new failure modes that Adrian Hornsby had created for his failure injection layer for Lambda. So first off, he added a status code injection, so you were able to inject specific status code into your application. And he also added exception injection, so you were able to create exceptions within the code. And then we also tested the functionality that he had added for rate control of failure. And rate control means that you were able to control how often the failure should happen. Not that it happened on every function invocation, but instead perhaps at 50% rate. And we also demoed the new Serverless Chaos demo app. The app, if you remember, looked like this. So we had a static content S3 bucket. We had an Amazon API gateway, and then we had the 3 Lambda functions. One that demoed latency injection, one for status code injection, one for exception injection. And then we had the Amazon DynamoDB table in the back. And this is what the demo app looked like now, the newer version. And this can be seen at demo.serverlesschaos.com if you want to have a look at it yourself. So that was last week's video, but now let's move on to this week. As I said, we're going to talk about disk space failure this time. And so let's start off by looking at storage for AWS Lambda. There are, of course, many different reasons why you want to store data within your Lambda functions. It might be temporary storage. It might be that you want to transform data and have to store it in between. It might be that you want to cache data so that it's quicker to retrieve it the second time. As you're probably aware of, you have access to 0.5 gig of storage within the temp directory. This can be seen in the service limits in the Lambda documentation. And this is ephemeral storage, and this is shared between multiple invocations of your Lambda functions. So that means that even if you call the same function more than once, they might have access to the same temp directory storage. And the same storage is used until the Lambda instance is recycled, or perhaps if load makes it needed to create a new Lambda instance, so a new one is deployed. And we as a user don't control when a new instance is started or when existing ones are being reused. This is done entirely by AWS in this case. So if we look at the question from the beginning, if we still need to think about storage when working with serverless, the answer is yes. We still need to think about storage because we have this 0.5 gig and we need to make sure that we use it in a correct fashion. So now we're gonna do a demo of this, see what it looks like. And I guess this is the easiest demo we've done so far. The architecture is just a Lambda function and that is using disk, and it is behind an API gateway, which can be called by the client. So extremely simple demo in this case, but it's gonna show how we work with storing data in the temp directory. So let's jump on over to Visual Studio Code as we usually do and look at what the function really does. So a Python function in this case, we first off just define the file name for a file to create. In this case, it's based on a timestamp so that we get a new file name each time. We create a text file in the temp folder, and within that we write the amount of free disk space that we have in the temp folder at the moment. Next step, then we read the same text file from temp, and just for fun, we list all available files within temp, and then we assemble this as a result, which is then in JSON format being a response to the API. So this is all that the function does. So fairly simple. We create a file, we enter the amount of disk space we have, we read the file, we list all files within temp, and then we create a response. So let's try this out. I have deployed it already, so it's available for us. Let's use Postman in this case, so it's simple to use and visualize what happens. So this is the API URL that we're using. So then I'm going to call the disk function right now, and let's see what the response is. There we go. So the response, we're getting the file name as response. We're getting the file contents in this case. So it's showing us that the free disk space is, well, 513 megabytes. And then we're also getting the folder contents that we have within the temp directory. But the interesting part now is what happens when we're invoking the same function multiple times. So let's try it again. Okay, we can now see that we have a new file name. The disk space is slightly less than it was before. And looking at the folder contents, we can now see that there are 2 text files. So these are different invocations of the same Lambda functions. And in this case, we're still using the same temp directory. So we're just creating new text files within the same temp directory. Now we have 3, now we have 4, and so on. And for each time, of course, the free disk space is decreasing. So we're having less and less free disk space. Since these are just minor text files, we might need quite a few of them to fill up this entire disk. But this shows quite easily how the temp directory works, that we're reusing the same one. And let's just say that we have an increase in load on this. Well, then it might spin up a new Lambda instance, so that we have 2 separate Lambda instances running at the same time. So each invocation might not have access to the same text files in the temp directory. So that also means that you can't use this as a persistent storage. You can't rely on that the text files are there for the next invocation. Okay, so now we looked at the serverless part of the disk storage. But you're not here only for serverless, right? You're here for chaos as well. So now let's look at the chaos part of this. That is, what happens if we get issues with the disk, that we're filling our disk for some reason. And that's what we're going to try to do now. So we're going to do disk corruption injection. And I thought a lot about how to do it in the fastest possible way, because we need to fill a lot of disk as quick as possible. Because as we know, Lambda functions are usually quite quick. And to be able to do the experiment, we need to have a lot of data quickly. So I decided upon using the disk duplicator command and run that as a sub-process in Python. So what I'm doing is using the dd command, as in this example. So duplicating data from dev0 into the temp directory, giving that a name and a size. So my question to you out there, is there a faster way of filling disk space? So if you can think of a faster way of doing it, please let me know, and then we can update this example and look at your way of doing it. But this was the quickest way I could think of, at least. So moving back to Visual Studio Code, but this time we're in my fork of Adrian Hornsby's FailureInjectionLayer. So you probably recognize this by now. This is where we have the code for the delay injection, or the latency injection. This is where we have the exception code or exception error injection, and this is where we have the status code injection. So I've created a new one that I'm calling corrupt disk space. And we need to have a way of configuring this as well, of course. So we're adding more stuff into the parameter that we're storing in parameter store. In this case, the file size. So we're able to set what size the file that we're gonna inject into the temp directory is. And then we're just using the dd command, as I showed you earlier, to create a file of this size within the temp directory. So when this is enabled and we're running it, it should create a file within the temp directory to help fill the disk for each invocation. And then we would probably get an error, and we can look at what that means and how our application handled this. So this is a new failure injection that we're adding to the layer. Corrupt disk space. So we're able to quickly fill the disk with space or with contents and make sure that our application handles that the disk fills. So let's try it out. And to try it out, then we of course just need to wrap our function with this new corrupt disk space function. So let's move over to the disk function that we looked at earlier. First off, we of course need to import from chaoslib, import star, and then we wrap it with corrupt disk space. There we go. And then we just need to deploy this with the updated code so that it's able to use the failure injection layer and the corrupt disk space. So while that is deploying, let's look at the parameter, the updated parameter that we have in SIP's Systems Manager parameter store. So this is the new one. It looks more or less the same as before, but with the added option of file size. And in this case, it has a file size of 100, which means that when we enable this, on each invocation, it will add a file that is 100 megabytes large in the temp storage. And that means that we will not be able to fill the disk on each invocation, but after a few invocations, it will fill up the disk. But this can, of course, be increased as well to another value if we wish. So with this in place, let's move over to Postman once again and just try the function once more after deployment. So we are invoking it, and yes, we are getting a response. Remember now that we haven't enabled the failure injection, so far it's just doing what it did before, but we have now wrapped our function with the corrupt disk space, so we should be able to enable it. So let's try that out. And we can do that as usual using the CLI. I have prepared it here. So now just change from is enabled false to is enabled true, and file size is 100 megabytes. There we go, we have a new version. So let's try it out now. Cool, still working. We have free disk space 513 megabytes. And let's invoke once more. Oh, there we go. Now we can see that we have free disk space 413 megabytes. And in the temp folder, there is now a new file called corrupt disk space and the timestamp, which should be around 100 megabytes large. So let's invoke it a few more times. A new one. We're down to now 213 megabytes. And now we're at 113. Now we should be at... There we go! We're getting an error. So now we have filled up the disk and we're getting an error. That's cool. So now we have performed our experiment and we have filled the disk with files and we're getting an error. So let's switch over to CloudWatch and look at the logs for this function. As you can see, we have two different streams. The first one is the one where we had the original code without the corrupt disk space wrapper, but this should be the new one. To begin with, it's working as it should. It is corrupting with a file size of 100, and we can see that it's copying about 105 megabytes in 1.3 seconds, which is quite fast. Scrolling down, and then we're starting to get errors. Here we go. It is corrupting, but when it's calling the sub-process, the DD, it is getting the error as we had before. So it's not able to create the temp file that we needed. So that's the first error. Let's then run it once more. Still error. So let's just wait for the logs to update. There we go. Now on the second try, we're getting this error message. So OS error number 28, no space left on device. Okay, so that was pretty cool. We were able to inject disk failure into our Lambda function by having a wrapper that filled the disk with contents. So with this demo example, we were able to see that our application, or in this case just the function, couldn't really handle that the disk space filled up. So we just got an error from it and weren't able to continue. But this is just the beginning when doing these experiments. Now we found something, then we need to work on it further. So a few things to consider then. First off, if you're disabling corrupt disk space, doesn't mean that it will clean up the temp. So the off switch in this case just means that it won't continue to fill the disk. So that's an important note. And more on the serverless side is you should consider cleaning up the temp directory within your functions if that is possible. Of course, if you're using it for cache purposes, you want to keep whatever you are storing there, but make sure to clean up things that aren't necessary so that you're not filling space without the need. And make sure to handle the errors that are thrown if the disk is full. That's not usually the case, perhaps, but by doing these types of experiments, you're able to see what type of errors you're getting if there is a full disk. Also consider if there are other storage solutions that you can use instead of the temp storage. Perhaps you can use S3 or DynamoDB instead. There is, of course, a latency question around this as well then. And as always, make sure to have graceful degradation in your applications. If there are errors like this, make sure that your application can handle that so that you don't get a complete outage just because there is a problem with a function like this. Okay, thank you for watching to the end of the video. It has been fun looking at Chaos experiment for disk space in serverless environments using AWS Lambda. I want to say thank you to Adrian Hornsby, as usual, for his work on the FailureInjectionLayer. And thank you to my t-shirt sponsor for this week, Gremlin. Awesome. If you want to have your t-shirt on the next video, just send it to me. Make sure to follow me on Twitter and make sure to subscribe to the YouTube channel. Okay, thank you very much.